Hello, I'm Kyle. I'm the technical content developer at Maple Systems. Welcome to the Maple Systems video training series. High-speed counters are used in industrial automation and control systems to count events or pulses at a faster rate than normal counters. High-speed counters are designed to handle high-frequency input signals and are used in applications where precise counting and timing are essential. A high-speed counter is used to capture the state of the inputs for a PLC or I/O module, and they are used to count the number of pulses received in an assigned high-speed digital input. So what is the difference between a high-speed counter and a normal counter? A normal counter increments by 1 for every clock pulse, whereas a high-speed counter is rapid counting. Speed is usually not a critical factor, whereas high-speed counter features the ability to filter out noise, handle rapid changes, and provide precise counting accuracy at high speeds. A normal counter has a specific max counting frequency. It can usually only handle a few hertz, whereas a high-speed counter can usually handle a max frequency of 100 kilohertz. And so a normal counter is used for conveyor systems, packaging machinery, traffic control systems, whereas a high-speed counter is used for automated robots or CNC machining, high-speed sorting machines, as well as high-speed filling machines. In industrial automation, high-speed counters are used in manufacturing industries to count products at a high speed on the assembly line or monitor machine rotations at a high speed. It is also used for motion control. In robotics or CNC machines, high-speed counters are used to keep track of encoder signals which provide feedback about the position, speed, or direction of a moving part. So, what would require a counter that works at high speeds? High-speed devices or high-accuracy devices. So we know a high-speed counter is integrated into the control system, often within a PLC or dedicated high-speed counter module. That counter is configured to receive and process the pulses generated by the encoder. So as the encoder generates pulses, the high-speed counter counts the pulses to determine the position and speed of the rotating object. The counter can also analyze the order of pulse transitions, rising and falling edges, to determine the direction of movement, forward or reverse. A fast counter is used to count the number of pulses a fast input has received. The high-speed counter is used to capture signal inputs. Normal inputs typically will not have the scan cycle, which is also input frequency, that will allow to count these signals. So, an encoder is therefore used. Now, what is an encoder? Encoders are sensing devices whose purpose is to provide feedback of the motion of objects to control systems. This feedback allows the control system to establish whether the object being monitored is being correctly moved or positioned, and permits adjustments to be made or actions to be taken on the movement and position of the object. Encoders are typically used to measure one or more specific parameters about the object, like a DC motor, for example. It measures parameters like position, direction, speed, or provides a count of the object or related value. Two main types of encoders are linear and rotary. Linear encoders deal with the movement of objects along a path or line. This type of encoder makes use of a transducer to measure the movement or distance between 2 points, sometimes employing a cable or a small rod. In these cases, a cable is run between the encoder transducer and the moving object. As the object moves, the transducer gathers data from the cable and produces a feedback signal that is used to establish the object's movement or position. Rotary encoders are used to provide feedback about the movement of a rotating object or device, such as a shaft of a motor. The rotary encoder converts the angular position of the moving shaft into a feedback signal that will then enable a control system to establish the shaft's position or speed. So, rotary encoders may contain shafts, but can also be known as hollow shaft encoders, or an alternate name is a through-bore encoder, meaning they are capable of being directly mounted on top of a rotating shaft, such as a motor. Absolute encoders are used in applications where knowing the exact position of an object is important. They are used in situations where the machine or process is inactive for a large percentage of time, or moves at a very slow rate. Also, even if power is lost, the absolute encoder by its design can determine the position of the object, since there is a specific digital signal associated with every position. Incremental encoders use a simpler method of counting movement and rely on establishing the position of the object by counting the number of pulses and then using that count to compute the position. Because they rely on pulse counting, there is no unique digital signature that can be used to determine an absolute position. Hence, in the event of a power loss, Incremental encoders must be referenced to a home position or reference point that the counter can be reset to, and then used to compute relative movement. One way to think about the difference is that incremental encoders measure the relative movement against some point of reference, whereas absolute encoders measure the position directly using unique signal code that directly reflects the position. So here is an incremental optical type of encoder. It uses a beam of light that passes through a disk that has opaque lines in a specific pattern. On the other side of the disk is a photosensing device that will interpret the light based on the pattern in the disk. The pulses of light are then converted to electrical signal. This is sent back to the processor, which in this example is a Maple PLC connected to a high-speed counter module. This is done through the encoder's output. How does the PLC interpret the signal? Well, there's something called a single phase. There's a single phase rising edge counter and a single phase falling edge counter. These are types of digital counters that count events or pulses based on both the rising and falling edges of a single input signal. Rising edges refers to transitions from a low voltage level to a high voltage level, while falling edges refer to transitions from a high voltage level to a low voltage level. The counter is triggered to increment on both the rising and falling edges of a single input signal. This input signal is typically a square wave or a pulse. Each rising and falling edge of the input signal causes the counter to increment by 1. The counter keeps track of the total number of rising and falling edges it has detected. So how can we get more precision from a single phase counter? It would be utilizing a single phase rising and falling edge counter together. So the counter is triggered to increment on both the rising and falling edges of a single input signal. And there's also a two-phase counter. So how do these work? So a two-phase counter typically refers to a type of digital counter circuit that operates in two phases, the up phase and the down phase. So during the up phase, the counter increments its count. It counts up by 1 for each clock pulse received. The clock pulse is the input signal that drives the counter. During the down phase, the counter decrements its count. It counts down by 1 for each clock pulse received in this phase. So the two-phase counter usually has two sets of outputs, one for the up count and another for the down count. These outputs represent the current count of the counter. While single-channel encoders can be used to establish motion and movement, they have a limitation of sensing the direction of movement. Therefore, the output of the encoder cannot detect the direction of rotation, only the magnitude of the motion. This limitation can be limited by using a quadrature encoder. Quadrature encoder signals generate two square wave signals, often referred to as channel A, phase A, and channel B, phase B. These signals are 90 degrees out of phase with each other. The quadrature counter counts the pulses from both channel A and channel B. Each rising or falling edge of these signals represents a pulse. So by analyzing the sequence of pulses on channels A and B, the direction of rotation can be determined. For example, if channel A leads channel B, the rotation is in one direction. And if channel B leads channel A, the rotation is in the opposite direction. Here is the high-speed counter configuration window in MapleLogic. To open this, go to Program, right-click on Program, select New Program, and then under Special Configuration, select HSC, and then hit OK. Previously in the video, I went over the different phases. Well, here is where you would choose either a one-phase or a two-phase. And this phase right here, two-phase 4 multiplication, this is for a quadrature encoder. And here for count mode, this is where you would choose either a linear counter or a ring counter. So linear is used for one directional counting, so single phase, also known as a binary counter or an up counter. A ring counter forms a closed loop. You would use this where a rotating sequence is needed. This is usually used for a rotary encoder. Compare mode for a linear or ring counter is used where the current count is compared to a preset value for a linear counter. When the count value matches the predefined value, a specific action can be triggered, such as generating an output signal and resetting the counter. A ring counter would involve checking the current state of the counter against a reference state. So, in summary, the compare mode in both linear and ring provide a way to trigger actions when the count reaches a specified value. And down here is your unit time and setting up your pulse per 1 cycle, and then whether or not you're using RPMs or pulse per second. So pulse per second and rotations per minute can both be used for either reading pulses from an LED light, for example, or rotations of a motor, for example. So this is all I'll be covering today In the next video, I'm going to be doing a live demonstration of connecting a Maple PLC to a motor and rotary encoder while utilizing the high-speed counter configuration window here in MapleLogic. I hope you enjoyed this video, and thank you for watching.